Hello and welcome back to Calculus 3. This is part 2 lecture notes for, lecture for our integrals in cylindrical and spherical coordinates. Before we jump into spherical, which is on the menu for today, we are going to take a look at another problem which I posed earlier at some point. This is going to be a cookie that has 8 petals, and I said this is 2, and the cookie is going to be 1/2 inch tall, and I want to know the volume of that cookie. So to graph this, we are going to use cosine of 4 theta. So R is equal to 2 cosine 4 theta. The amount of petals is 8. Divided by 2 is 4 because the even numbers double for petals and odd numbers stay the same. So we model this problem immediately by 2 cosine 4 theta, which is what we learned in Calc 2, basics of polar functions. And now for volume, we are going to use triple integral for cylindrical coordinates because we have we have dr, d theta, and then there is a height of the cookie, which is z. Now I took the top and the bottom of the cookie to be flat. We can also have some design on top of the cookie, so that could be some other function, and so on, but this is an introductory problem, so for modeling. So volume is triple integral, the z, r, dr, d theta. Z is from 0 to 1/2 in inches, because that's just the height. You have a flat bottom of the cookie, flat top of the cookie, they're 1 inch apart, so 0 to 1/2 on z-axis. The plane that cuts the cookie, and then our R equation is going to be from 0 to 2 cosine 4 theta, and we want the entire cookie, all 8 petals, so 0 to 2 pi. So that would be the setup for the cookie, and now we can quickly compute this. So when I integrate z, it will be a double integral of z from 0 to 1/2 r dr d theta 2 pi 2 cosine 4 theta 0 0, and then we would have 1/2 can jump in front, double integral of r dr d theta 0 0 2 pi and 2 cosine 4 theta. Now we're going to integrate r. Integrating r, we're going to get r squared over 2, so I'll kick the 1/2 outside, and I will just have r squared computed from 0 to 2 cosine 4 theta, and I still have d theta to deal with. So now when I plug in the function, I'll have 1/4 integral 0 to 2 pi, and in this case I plug in this, so it's going to be a 4 cosine squared 4 theta d theta. Quarter will kill the 4, and when I integrate cosine square, I can't integrate cosine squared, I have to use power reducing formula from Calc 2. So that's going to be 1/2 integral of 1 plus cosine 8 theta, cosine 8 theta d theta from 0 to 2 pi. And now I can finally integrate this to 1/2. Integral of 1 is just theta. And then I have the integral of cosine is positive sine, and I have to divide by 8. So plus sine 8 theta divided by 8 from 0 to 2 pi. Now sine at any pi is always 0, so the whole term dies, and volume of the entire cookie would be pi inches. Pi inches cubed. Does it make sense to be pi inches cubed? Well, it kind of does, because it is the 8 petals, right? And it's only a half thickness. Pi inches is 3.14 inches cubed, so definitely can fit the cookie in the pi inches cubed volume. And then when you have the volume of the cookie, you can go do nutrition, and right, depending on, because the volume of the cookie gives you the mass and gives you the, you know, what ingredients you use to make the cookie, so you can come up with an entire thing on nutrition for it. Spherical coordinate. It's good to go on YouTube, guys, and look for videos that would visualize spherical coordinates. That's a really good advice, because this is a coordinate system you haven't dealt before with, and in this coordinate system, we do have our polar as a base, but we are also adding another angle, and the spherical coordinates now are changing notation just to make things even more annoying. We're going to have rho, phi, theta as our, so rho, phi, theta is for the coordinates, and we need to understand what these coordinates are in our x, y, z realm. So if I am to put a point somewhere and call that point rho, phi, theta as the coordinates in a spherical coordinate system, that point will drop somewhere on the xy plane and create an angle with the x-axis. So the angle with the x-axis is the angle theta. The angle with the z-axis is going to be phi, and the length of the arc, well, the length of the arm is rho, which is the radius. So this is radius. We used to use r before, so now for the first time it's rho. Angle with z-axis and angle with x-axis. Now what's important is that the first and the third, so this one and this one, you know what, I'm gonna do this way. Rho comma theta is equal to r theta, I'll just say polar base, because the way you find a point in the spherical coordinates is you draw the radius along x-axis. Well, that's what you did for this one, and then you swing theta in the xy plane from z, so that's exactly what you did, and then you finally go up the y-axis. Now, I'm asking you to find videos to visualize this online, because the video that I'm having over here obviously can't picture what I'm going to show you in class now. So this is the way the coordinates work. You see, there's the origin of 0, 0, 0, and there's the z-axis, right? So now, if I go along x-axis and I create some radius along the x-axis, and then I swing that axis on the, swing that radius on the theta, and then towards z, I come up with a point in space. So one more time. I draw the radius out along the x-axis, then I swing that theta, which is the same procedure you have for polar coordinates, r theta, now it's rho theta, and then you swing up to meet the angle with the z-axis, right, whatever angle you have, which is angle phi, which is the one in the middle. These are called spherical coordinates because when you pick a point in space and you put the 0, 0 in that space, the range of motion around that point in space will actually create a sphere around that point. Because due to the two angles, I am allowed to go anywhere, right? And it will create a sphere, and then the farthest the sphere gets is the equator, which is when my arm lays flat on the xy plane, but then I can go below and draw also the second half, right, with the angle with the negative z-axis. So with these particular coordinates, being that the rho doesn't change, I'm reaching all points of the sphere above and below xy axis. And these coordinates are tough to work with because there is no direct and easy conversion from rectangular to spherical realm. If you have your problem given in rectangular coordinates x, y, and z, and you want to go to spherical coordinates, well, if it's just not a sphere or a half a sphere or something that is cheap like that, it can be very, very difficult to, because you have to do a lot of side trig and look at triangles and things just to figure out conversion, because it depends what you get. Where spherical to rectangular, it does have formulas, but that's the one you don't need, actually. So even having formulas doesn't mean much. Generally, we deal in class, right, with the basic spherical integrals. We deal with the basic conversions with spherical integrals without going into some very deep conversions, just because that conversions are based on individual problems. There is no set of formulas that you can remember, like you have polar to rectangular, rectangular to polar in 2D. So the first thing we want to do with spherical coordinates is to obviously prove the volume of the sphere, because you know that the volume of the sphere you memorized 4 pi over 3 r cubed, but then you might have tutored someone before, and they say, why? Oh, great, let me show you why. Then you crank the triple integral in spherical coordinates to show to this 7th grader why the volume of the sphere is what it is. In order for us to crank that, we first have to write the spherical integral for volume. And then if you have anything to plug in, it will become 4D. So our good friend over here is going to be the integral of dv, since we are only talking volume at this point. And now the string becomes far more complicated, but we'll live through that. So we have a triple integral here. We have alpha, beta, a, b, and then g of phi and theta, and h of phi, and theta. And then here is the string which you are memorizing. String now is rho square sine phi d rho d phi d theta. This is a unit. Anytime you are working on a spherical integral, you have to drop that whole thing in there. If there is a function you're integrating, it will go here. Completely separate from the string. You know that you have r dr d theta as a string for polar 2D. You know that you have dz r dr d theta as a string unit for cylindrical coordinates. Now you have rho squared sine phi d rho d phi d theta as a string. Great. Let's go and deal with the first problem. The cheapest problem you can get in spherical coordinates is obviously to calculate volume of the sphere. The damn thing is designed for it, right? So, volume of the sphere with the radius rho equal capital R. We'll do the general formula. Obviously, if you are looking for the volume of the ball with the radius 3, well, that's rho equals 3, and you just plug that in. Great. So what do I have? I have a ball, sits in the x, y, z world, and I want to set up a triple integral in spherical coordinates. Now, I'm not computing anything inside, so I know that I just need to drop in the string rho square sine phi d rho d phi d theta. The inner integral is rho, and I just said that the radius should go from 0 to capital R because that's our radius. So the inner one is 0 to capital R. All right, now the tricky part. You want the full ball, right? All the way around the equator. Your d theta is going to go around the equator, right? So d theta is going to go around the equator in the xy plane, which is where the ball is the fattest, and it's going to make a full circle, right? So if it makes the full circle, then it's 0 to 2 pi. 0 to 2 pi to make a full circle of theta around the ball. Now what's happening with phi? That's the trick. It's 0 to pi. You see, please imagine that this rectangular keyboard is actually a disk, you know, like a CD. Actually, you know what? I'm gonna take the clock because it's exactly what I need. There we go. Beautiful. Oh, and they fixed the clock. I love it. And then the erase fixed me as well. Love it. Love it, love it, love it. All right. No, I love this place. Please look at the red line, red hand, the second hand. Second hand is going to go from the center, stretching out R, and as it goes theta around the clock, it will create this disk. So clearly, it has to go 0 to 2 pi to give you the full disk like this, right? Now look at this. If I rotate this only pi, do you see that the upper half is going to make upper half of the ball, and at the same time, the bottom right? So there is no need for me to go 2 pi all the way, right? You just see that what I did is I rotated half. I rotated 180. And then this part, the one that is closer to you guys, is going to trace the entire upper side of the ball, and the bottom at the same time is going to trace the entire bottom half of the ball, which is hemisphere, right? So as I turn this only half a rotation, 180 degrees, the whole ball is created. So that's why the inner integral is 0 to pi. And now you go and you are now integrating regular nested calculus 1-3 integrals, right? So integrate your rho first. You will get your cube from there. So that eventually becomes r cubed, and then you go from there.
Calculus 3 example. Spherical coordinates. Thanks for tuning in.
Highly. Well, I wouldn't go that far, but don't worry about it. So now we are integrating a rho, which means sine phi is a constant, right? So we have a rho cube over 3. Sine phi gets copied. We are computing this from 0 to capital R. I still have d phi. I still have d theta. When I plug this in now, 0, 0, 2 pi, and then pi. I plug in r. I get r cubed over 3. I have sine phi, d theta. Now when I integrate in terms of phi, then r cubed over 3 is a constant. You can actually kick r cubed over 3 in front of both integrals because that's just numbers now. Integral 0 to 2 pi, and when I integrate sine, I get negative cosine phi from 0 to pi, and I still have d theta to deal with. So this is r cubed over 3. Remember what I need. I just need 4 pi, and I'm done, right? I still have the integral of 0 to 2 pi, and now cosine. So this is going to be negative cosine of pi plus cosine of 0, d theta. Well, what's the cosine of pi? It's negative 1, right? And the negative in front is 1, and then plus 1, it's 2. So this whole thing over here is equal to 2. And that is going to kick out and become 2r cubed over 3. And I have integral of d theta from 0 to 2 pi. That's just going to be 2 pi. So I have 2r cubed over 3 times 2 pi to give me 4 pi over 3 r cubed as the, and we know that's the volume of a sphere. Right, Greeks did it with a stick and a rope more than 2,000 years ago. So we're good to go. This is the cheapest problem, obviously. These coordinates are designed to work with spheres. And now we go and take a look at some problems that we can work on. So now a problem which says integrate triple integral. The region D over here is equal to first octet. Guys, that's positive x, positive y, positive z, right? It's 1/8 of the space. Of x squared plus y squared plus z squared raised to the -3/2 dv. So that's the problem. Note that you have a function inside, so you are dealing with, you have a function inside, you are dealing with the 4D situation. You have 3 integrals and then the function, so that's 4 dimensions. Now, what am I going to do here? Well, we already know that if we are to use limits from the circle, from the ball that they gave us, we are going to run into the issue of, oh wait, they give us the first octet between 2 spheres centered at the origin, radius 1 and 2. That's extremely important. So first octant, so first octant with rho equals 1 and rho or maybe I should say between rho equals 1 and rho equals 2. There we go. So what do I have? Well, first off, I'm going to write this in blood. Rho square is equal to x squared plus y squared plus z squared. That's the ball sphere centered at the origin 0, 0, 0. So I immediately know how I'm going to transform the middle of the integral, right? The integrand. So I am working in the first octant, and all I worry about is this shell that we are getting from 1 to 2. If avocado was perfectly round, you cut avocado half, take the middle out, right? And then you cut another half, so that will be an 1/8 of the avocado. So that's what you get, that shell, right? It will look like a triangle from a side, but you know it's round and it's, right? I should have brought an avocado. Well, when I cut it, I would cut it this way, and then the part that I would have would be round, the top part.
You get special avocado. Special round up, special spherical.
No, they are.
We talk about a cantaloupe, and they don't have it inside, they have to take out.
The point is the inside though.
Well, we're gonna cut. Yeah, when you scoop with a spoon. It's just I don't like cantaloupes, so that would never occur to me.
And the orange that sliced already for you. Just gotta peel it first.
Yeah,
But that will be that will be the entire. I need a half with a carved inside. So it needs to be. Think of the ball that has the like there is a core on the earth. Earth is round, it's a ball, right?
It is.
So it's not, well, it's very close to a ball. All right, so what do we have here? As I am setting up this integral, triple integral, you see that I get to move this square as a square root on the other side, which is a half. So I'm getting rho to the -3 over here. Are we all green on that? So rho to the -3, because the whole thing with the 1/2 is going to be rho, and then I just have rho to the -3. And then I have the rest of the string, which is rho squared, sine phi, d rho, d phi, d theta. So that's the setup. This puppy over here is your function f. The rest is the string that you are memorizing and dropping in there. Now, limits. Well, rho is clearly from 1 to 2. That was given to us. And now I just need to figure out the eighth of a circle. So what are the limits that I have? Yes?
It's going to be for theta 0 to pi over 2 and for
Excellent.
phi 0 to pi over 4.
Now, why would phi be 0 to pi over 4?
Well, my thought is that because you can't really create the exact region there because you're involving the entire disk. Oh, wait. I don't know. My thought was like basically how you were saying with the disk we create.
You don't have a disk now.
Yeah, it's just
You just have a slice now.
So it would be pi, 0 to pi over 2.
0 pi over 2. So this is where spherical coordinates get tricky, because you would like it to be, right? The same like for the sphere, but for the sphere, you had a disk. One half of the disk did half of the ball, the other half, right, created the second half of the ball, so it was only 0 to pi. Now you don't have a disk, you just have a little slice, and then it will be going the entire way. I'm not sure if the picture from the book helps, but I'll show it anyway. So this is the drawing that I have and I gave up. Now this is the one where they show the slicing. So you see your theta goes from x-axis to y-axis, and those two axes are 90 degrees, so 0 to pi over 2 on theta. Bravo. And then this brown, light brown, whatever the hell this color is, same like my shirt, actually. Yeah. So this thing needs to stand up to draw all of this yellow or orange. What the hell are these colors? Just give us a 16 palette. What is this? Call this orange, call this brown, and it's red and it's blue. It's good. So the brown part from this will cover, as you can see, the entire angle between z-axis and the xy plane. And they're 90 degrees to each other, so it's going to be pi over 2 to travel there. When you multiply two rows, you get the, you add their exponents. So the final integral over here that we are looking at, 0 pi over 2, 0 pi over 2, 1 to 2 of 1 over rho sine phi d rho d phi d theta. And I mean, it's obvious the answer is pi ln 2 over 2. I mean, that's clear. They solved it over there. I just copied the answer. You can integrate one by one. Are you ready for the ice cream cone? I'm sorry?
Did we already do that with cylindrical coordinates?
Yes. Now we can do it also with spherical. And the spherical coordinates are actually going to add the cup on the top, right, as a part of the sphere. For cylindrical coordinates, you had the flat z, right? It was not rounded. So technically what you are doing is you're going to make a circular cut that is going to go conically to the center of the ball, of the sphere, and just take that out. And when you take it out, it's going to look like a cone, but it's going to have the curvature of the sphere on top rather than having a flat Z like you had for... so that's the difference between the two cones. I know, it's amazing, right? So the cone we look at right now is going to have a hat, right? It's going to have a hat. And we are going to have this cone centered at the origin, right, with a peak there. This height on top over here, let's say it's 4, will actually give us the radius of the sphere that creates this cone. And I also need to know how much am I cutting over here inside. So let's call this pi over 6, 30 degrees cut inside. So it's actually 60 degrees across. So what's the volume? Well, the value on the z-axis is 4, which means rho equals to 4, which is a sphere. And now, when I set up my triple integral, I'm not using any functions because I'm looking for the volume, so I just go with a string, rho squared sine phi d rho d phi d theta, and rho is from 0 to 4 because I want the full content of the cone. And now the phi angle is 0 to pi over 6 because that's how much you go away from the z-axis. That's what measured by phi. And 0 to 2 pi on theta because I want to have the entire cone, right? You can cut the cone in half and just have half a cone, vertical cut, through the half a cone 0 to pi, let's say, right? But I want the full cone, so 0 to 2 pi on theta. And all you need to do now is to integrate. Again, you're integrating rho, copying sine phi, so it's the same. And obviously the answer over here is 64 pi over 3, this is obvious, times 2 minus root 3. So when you integrate one by one, you will get this answer. Now, obviously, it's worked out in a book, so you can look at it. Yeah.
How do you get the rho squared sine phi? Is that like given with the?
That's the string. Okay.
Welcome to the class.
Thanks. Just like already did it, but.
Yes, excellent.
Yeah,
Just like that. But this is for the spherical only.
Yeah.
All right, good. Good.
They don't use rho on the theta in the book.
I'm sorry, you can just...
Do they use different variables in the book?
No. The rho phi theta. That's what they use.
It looks like double UX and U on the exam.
Which page are you on? 1059. I have rho, phi, and theta. And I'm actually going to make the trip.
That is some conversion over there. Yeah, because
I mean, I don't know. It's probably a web browser messing up something. Did you click translate at any point or something? Because this is this is what I see on the same page. It's the same book. Rho squared sine phi, right? Yes. So it's something with the browser in that case. Try opening on the phone, please. The phone. Sure, you have a Google Chrome on the phone, or something. So try opening the same page on the phone and see if everything is okay there. But as you can see it, and you can actually see that the formatting is not the best. That P is way too big for the. So that's something that is definitely glued over what it was supposed to be there. All right, good. So I have, I think, one more problem. We're going to hit the break after that. Just need to find where the stuff is. There it is. Okay. So what are the spherical coordinates good for? What are the polar coordinates good for? What are the cylindrical coordinates good for? They're good for round objects, right? They're good for round objects. That's what they deal with. Ball, right? Round. Your can, round. All of the shapes are round. What are they not good for? Well, they're not good for planes. You would argue, obviously, cylindrical coordinates have z, so, we just did it with a cookie. Bottom plane is z equals 0, top plane z equals a half. Yeah. Try a slanted plane in polar coordinates, in a cylindrical coordinates. You will know the meaning of pain, all right? It's not designed for it. So you want to stick with round objects, cylindrical and spherical and all of these kind of things. Now, can you do certain things? Sure. You saw that z equals a number, gives you the horizontal planes, like the floor and the ceiling, right? So, cool. We also have an equation for the flat plane in spherical coordinates, except it involves secant of phi, and it's just annoying as hell, right? So, if you want the flat plane equation, so flat plane, there we go, equation, in spherical coordinates, which obviously looks like x, y, z, so we're just going to have a plane over here that is going through the value on the z-axis, and that value is going to be called a. The equation is rho equals a secant phi. And phi with limits is going to be between 0 and pi over 2. So that's the equation. Now, why is this important? Because we have a whole bunch of problems to deal with in the homework and in general that contain flat planes. So the problem 46, for instance, and this is the last problem we are going to take a look at, has this conical shape that is cut in with a sphere sitting in the coordinate system like so. The top is flat at 2 and the sphere cuts at 1. And this angle here that I should, this is a terrible drawing because this angle should cut in there and this angle should cut, well, now I gotta fix all of this. So draw the dashed lines, and then when these dashed lines intersect, draw the full lines, and then draw the bottom. There we go. So the sphere is going to cut into the object, and this is going to be pi over 4, they say. That's okay. So this is all we have. We have a 1, we have a 2, and all right, so from the bottom, we have rho equal 1, equation of a sphere which is cutting into the shape from the bottom. So the bottom is scooped out, all right? You know, you take a scoop the ice cream out, and you're left with that negative sphere. That's what you have on the bottom. You have a negative sphere. The top is flat, which means rho equals 2 secant phi. So flat plane on top. Now in any other integration you would just call it z equals 2, right? But simple z equals 2 in any other coordinate system is a living nightmare over here of 2 secant phi. And now we are supposed to set up the integral. So to find the volume of this, we set up our triple integral. We have our rho square sine phi d rho d phi d theta. The object is full round on theta, so 0 to 2 pi on the edges. The angle of pi over 4 is given to us for 0 to pi over 4, which is the phi limits, and then a rho, well, bottom is 1 and a top is 2 secant phi. Now this problem is not solved in a book, so I guess I can't give you the obvious answer, so we'll have to integrate this one. So double integral for the outer. When I integrate rho squared, I get rho cubed over 3, computed from 1 to 2 secant phi. Oh, I'm going to regret this very quickly. Sine phi d theta. 0 to 2 pi, 0 to pi over 4. And now I have to plug in this stuff. You know what? I'm going to kick 1/3 outside because I can. So I have to deal with that at least. I have 8 secant cube phi minus 1 times sine phi d theta. This is further equal to 1/3 integral 0 2 pi over 4, and then we're multiplying sine phi, so this is going to be 8 sine phi over cosine cubed phi. I have to switch this secant because there is no integration pair secant sine. There is integration secant tangent, there is cosecant cotangent, and then there is sine and cosine. You cannot integrate, right, secant sine. Minus sine phi d phi d theta. Now, to integrate the next step over here, we are clearly going to use basic u substitution for this one, because we have cosine cubed in denominator. So u equals cosine phi du equal sine phi d phi, which is exactly what we have. So this becomes 1/3 integral of 0 to 2 pi. And now I have to plug in my limits into the equation here so I can change them. When I plug in 0, I get 1 on the bottom. And when I plug in the... oh, hell, but then I have the second integral over here that's not going to use the same limits. Okay. In the parenthesis now. I have integral of 1 to, when I plug in pi over 4 root 2 over 2 of 8. And I have du over u cubed. And then I have minus the integral from 0 to pi over 4. So this one I'm not changing. This is just sine phi d phi. And then I have d theta next. So a little bit of annoyance, but not that much. 0 to 2 pi. Integral of u to the negative 3 is u to the negative 2. Divided by negative 2, so that makes a negative 4. And so negative 4 over u squared. Computed from 0 to root 2 over 2. Integral of sine is negative cosine, so plus cosine of phi computed from 0 to pi over 4. And still have d theta at the end. It is a negative sign. Right there, right? So that's what kills it. Yes. Because I was looking at it and I'm saying I can't put 0 into u squared. That was crucial piece of information. All right, so now when I plug in this, I get negative 4 divided by square root of 2 over 2 squared. Minus and minus gives me plus of 4 over 1, so that's just 4. Plus cosine of pi over 4 is root 2 over 2. And then minus cosine of 0 is 1 d theta. Holy nightmare. Compute all of this mess. 0 to 2 pi. When I square this, I get 2 over 4. That's a half, so that's a negative 8. Plus 4 plus root 2 over 2 minus 1 d theta. This is going to be 1/3 times negative, so it's a 5 plus root 2 over 2. And then you have integral 0 to 2 pi d theta, which is going to give you 2 pi. So this becomes 2 pi over 3, 5 plus root 2 over 2. Let's say that's good. You can redo these calculations and verify this. That's all the examples. I just want to show something, guys. To find the shortest distance on the surface of the planet between two cities, you have to involve center of the Earth. And the path between those two cities we'll call geodesiac, and that's the shortest distance on the, and it's curved path. So when you are dealing with flat spaces, like this floor, the shortest distance between point A and point B is a straight line. On the surface of the planet, or if you take just a baseball, the shortest distance between 2 points is not going to be the straight line. And there is a great graphic to show that. This is Seattle and Rome. If you have these 3 points, one at Seattle, one at Rome, and the center of the Earth, you can put the plane through those 3 points, right? We know 3 points is all you need. And then when that plane cuts the surface of the Earth, that is the shortest distance between the two, right? And as you are flying overseas, you will see that the trajectory of the airplane is always curved rather than a straight line. Because remember, when you are in a curved space, like on the ball, if you go straight, then you have to actually go with the curvature of the Earth, and you are going up on a bump, right? But if you go a little bit on top, you are not going as high on the bump, so you compensate. So that's why it's a little bit tricky if you never thought of that. I can also show you another. I mean, obviously, airlines will be doing these calculations very carefully to conserve the fuel and make sure they don't run out of fuel as they're flying between, right, over the ocean. Flight Radar 24, you don't have to sign up for it. You can if you love this stuff. Is a real-time airplane trace. And as you can see, it's busy, right? So these are the airplanes. If I pick, right, this is the now United States towards Europe. You can see the stream of airplanes going to Europe. If I pick any of these airplanes here, it will show me. Can't really see the trajectory here. I'm trying to see if I can. All right, that one has it. Nice. That one. You see it's not a straight shot. It's curved. So it's going to land somewhere in Europe. Well, actually in Munich, in Germany. So it's going to land right here. So it has a curved path to get there. Did not do this. See that? Right? So that's what you can do. The length of the curve as well and other stuff. So take a look at these things. All right, break time.